Fluid mechanics. Ever wondered why you feel lighter in a swimming pool or why deep sea divers need special equipment? It all comes down to one thing: fluid pressure. And today, we're diving deep into the fascinating world of fluid mechanics. Hey there, I'm Manuel, and in this video, we're exploring the core principles that govern how fluids behave. Whether it's the water in your shower or the air you breathe, understanding these concepts isn't just theoretical. It impacts everything from engineering design to everyday activities. The basics of pressure is simply a force exerted per unit area. In the metric system, we measure it in pascals, PA, which equals 1 Newton per square meter. But since a pascal is quite small for everyday applications, we often use kilopascals, kPa, or megapascals, MPa. Let me put this in perspective. Standard atmospheric pressure at sea level is about 101.3 kil or 14.7 psi pounds per square inch. That's equivalent to the weight of the entire column of air above each square inch of Earth's surface. Pressure in a fluid increases with depth. Think about diving underwater. The deeper you go, the more pressure you feel on your ears. This happens because the weight of the fluid above you increases with depth. For a constant density fluid at rest, the pressure change is given by delta P equals ρgh, where ρ is the fluid density, g is gravitational acceleration, 9.81 meters per second 2, h is the change in depth. This means pressure increases linearly with depth in a stationary fluid with constant density. If you descend 10 meters in water, the pressure increases by about 1 atmosphere. Types of pressure measurements. When dealing with pressure, we need to be specific about what we're measuring. 1. Absolute pressure. This is the total pressure measured relative to a perfect vacuum, zero pressure. It's always positive. 2. Gauge pressure. This is what most pressure gauges measure, the difference between absolute pressure and local atmospheric pressure. It can be positive or negative. 3. Vacuum pressure. This refers to pressures below atmospheric pressure and is measured by vacuum gauges. The relationship between them is absolute pressure equals gauge pressure plus atmospheric pressure. The mystery of fluid density. Density is mass per unit volume, typically measured in kilogram per meter 3. Water has a density of approximately 1,000 kilograms per meter 3, while air at sea level is about 1.2 kilograms per meter 3. That's over 800 times less dense. Density plays a crucial role in determining how objects interact with fluids. Consider a wooden block with a density of 700 kilograms per meter 3. When placed in water, it floats because it's less dense than water. But drop it in mercury, density 13,600 kilograms per meter 3, and it will float even higher. Here's where things get interesting. Density isn't always constant. It can change with temperature and pressure. For instance, hot air is less dense than cold air, which is why hot air balloons rise. This variation in density leads to fascinating phenomena like convection currents that drive our weather patterns. The challenge of pressure measurement. Measuring pressure accurately presents unique challenges. How do you measure something you can't directly see or touch? Imagine you're designing a dam. Miscalculating the water pressure could lead to catastrophic failure. Or consider a deep-sea submarine. Precise pressure measurements are literally a matter of life and death. Various instruments have been developed to tackle this challenge. 1. Manometers. These simple devices use columns of liquid, often mercury, to measure pressure differences. The height of the liquid column directly indicates pressure. 2. Board-on tubes. These mechanical devices use a curved tube that tends to straighten under pressure, moving a needle across a calibrated scale. 3. Pressure transducers. Modern electronic devices that convert pressure into electrical signals, providing precise digital readings. Each method has its advantages and limitations. For instance, while manometers are simple and reliable, they're not practical for very high pressures or portable applications. Buoyancy, the uplifting force. Have you ever noticed how much lighter you feel in a swimming pool? That's buoyancy in action, one of the most fascinating aspects of fluid mechanics. Archimedes discovered the principle over 2,000 years ago. Any object immersed in a fluid experiences an upward force equal to the weight of the fluid it displaces. The buoyant force is calculated as Fb, or F, G, and V, where Fb is the buoyant force, ρf is the fluid density, G is gravitational acceleration, V is the volume of fluid displaced to Varn. This principle explains why ships made of steel can float despite steel being denser than water. By shaping the hull to displace a volume of water whose weight exceeds the ship's weight, we create sufficient buoyancy to keep the vessel afloat. But buoyancy doesn't just make things float, it's also crucial for stability. Consider a submarine. When it needs to dive, it takes in water to increase its weight. To resurface, it expels water to become lighter. This delicate balance between weight and buoyancy allows for precise depth control. The stability problem. Speaking of stability, it presents another fascinating challenge in fluid mechanics. How do we ensure that floating objects remain upright? This is where the concept of metacentric height comes in. For a floating body to be stable, its metacenter, a theoretical point, must be above its center of gravity. The greater this distance, called the metacentric height, the more stable the vessel. Ships designers face a constant trade-off. A high metacentric height provides stability, but can make the ship roll uncomfortably in waves. Too low, and the ship risks capsizing. This becomes especially critical in design applications. Oil tankers need to maintain stability as their cargo shifts. Sailboats must stay upright despite wind forces. Floating platforms must remain stable in rough seas. Pressure in moving fluids. So far, we've discussed fluids at rest. But what happens when fluids accelerate? When a fluid accelerates, the pressure distribution changes. In a fluid accelerating horizontally, the free surface tilts, which is why water in a car sloshes backward when you accelerate. For a fluid in a container that's accelerating horizontally with acceleration x, the free surface slopes at an angle theta, where tan theta equals ax bar g. This explains why water in a tank truck shifts dramatically during acceleration and braking, creating dangerous slosh forces that can affect vehicle stability. Even more fascinating is what happens in rotating fluids. When a fluid rotates, centrifugal forces push the fluid outward, creating a parabolic surface. This is why when you stir coffee in a cup, the surface forms a slight depression in the center. The hidden forces in fluids, beyond the basic principles we've covered, fluids exhibit other important properties. 1. Surface tension, the elastic-like property of a liquid surface that allows some insects to walk on water and creates water droplets. 2. Viscosity, a fluid's resistance to flow. Honey has high viscosity, water has moderate viscosity, and air has low viscosity. 3. Compressibility, how much a fluid's volume decreases under pressure. Liquids are nearly incompressible, while gases are highly compressible. 4. Cavitation, a phenomenon where rapid pressure changes create and collapse vapor bubbles in a liquid, potentially causing damage to equipment. These properties interact in complex ways, creating both challenges and opportunities in engineering applications. Real-world applications. The principles we've discussed aren't just theoretical, they have countless practical applications. Hydraulic systems in vehicles and machinery multiply force through pressure transmission. Hydroelectric dams convert the potential energy of water into electricity. Aircraft design relies on understanding pressure distribution to generate lift. Medical devices, like blood pressure monitors, use fluid pressure principles. Weather forecasting depends on atmospheric pressure patterns. Understanding fluid statics and dynamics has enabled humanity to build incredible technologies, from the simple water pump to spacecraft that can withstand the extreme pressures of space travel. Bringing it all together. Fluid mechanics represents one of the most fundamental and practical branches of physics. The principles we've explored, pressure, density, buoyancy, and stability, form the foundation for countless engineering marvels around us. Next time you're on a boat, taking a bath, or even just drinking through a straw, take a moment to appreciate the complex fluid mechanics at work. These invisible forces shape our world in profound ways, even if we rarely stop to notice them. Thanks for diving into fluid mechanics with me today. If you found this helpful, check out our next video on fluid dynamics, where we'll explore how these principles apply to moving fluids. Hit subscribe so you don't miss it.